Okay, so if we compare the scores that we got, we can say here that the most, yani the best option in our case was the solar system with a grade of 0.7. If we take the other alternative, let's say hydro and wind, it's also good. Yani the scores are similar, 0.65, 0.647. So these three options here were the best. For wind and solar in general, when we say combining wind and solar, it might be a very good option. But here we got the lowest score because of the high cost and because we gave a high importance to the value of the cost that we have. Okay. In general, we can take many other parameters to help us into making the decision. And for example, the CER might be much more important to consider because it's true that we are putting a high investment, but we are having a much higher production and we might have a much larger CER. That's why we can take other factors to have a better idea about the strategies that we are doing. Okay. And now let's say we selected, for example, the solar system and we want to decide on the selling price, for example. Okay, so if you remember in any project before, okay, we decided now on solar and we want to do a parametric study, if you want to consider what is the range of selling prices we can take. Is it possible, for example, we can re-question some aspects? So can we reduce the maintenance? Can we reduce the initial cost? So you know that the design process is an iterative process. So you can also always go back to zero and try to enhance, or let's say, if not to zero, you can go back some steps and try to enhance your system, or let's say add maybe some a certain engineering approach in order to enhance the efficiency, etc. So you can always reiterate whenever you do the design process. So now let us consider, for example, that we decided on the solar system and we want to get, let's say, we have the numbers and we'll do some economical analysis to decide on the selling price that we should consider. So we'll give the following issues. So first, let us consider that we will select a solar system, a 3 kilowatt system. With a cost of 4,000 euros per kilowatt. It's not here the same example because in the matrix I considered any numbers. We said it's $7,000. So just it's an example if you want to practice on. It's not related directly to the same example we considered in the decision matrix. So it's 4,000 euros per kilowatt. And we have concerning maintenance and operational costs are telling us that for each year, the maintenance cost is equal to $100. We'll have to approach here. We'll compare two cases. If we have constant costs and in case we have variable costs, okay? So in part A, we'll consider that the maintenance cost is $100 and the operational cost is $150. While for part B, we'll vary the maintenance cost with years. So we consider, for example, that for the first year, we have a maintenance cost of $50. So C1 maintenance equals to 50. And for the second year, For the second year, the cost will be $75. And for the remaining years, we have a cost CI maintenance of $100. While the operational cost will remain $150. Okay, and the operational cost will be the same for all years, $150. Now, first, we want to study the life cycle cost of this system. So, first question, study the life cycle cost. When we talk about the life cycle cost, we don't include the incomes, so just the total cost for the lifetime. Okay, so considering, so they should mention for us, of course, the lifetime of the system for 20 years of lifetime. So as usual, whenever we want to calculate the life cycle cost, we need to consider for year 0 the initial investment, okay? Plus, in general, guys, always we consider that the investment is paid at year 0, and the remaining costs are considered to be paid, let's say, at the end of the year. This assumption is not 100% valid, because sometimes you have costs that should be paid at the beginning of the year, or you have, let's say, like salary, you have costs that should be paid in between. If in general, when we don't mention anything, we assume, we take the assumption of considering all costs paid at the end of the year, and whenever we consider the discount rate, we should divide by each year by 1 plus A. Okay, now in case in the given they told you, for example, the cost should be paid at the beginning of the year, then you divide by 1 plus A to the power I minus 1. Okay, so the whole issue is to consider if the cost will be paid at the beginning or at the end of the year. And it's in both cases, it's an assumption, because always we have costs that will be paid progressively. And for salaries, for example, you will pay them progressively. Okay, or let's say if you want to buy diesel for operation, let's say, also it will be maybe each month you can buy a certain amount. Some industries consider no, we cannot. We should always consider that we have the cost for the whole year to be on the safe side. So in case they tell you in the given a cost should be paid at the beginning of the year, then you should divide by 1 plus A to the power I minus 1. Unless, if they don't mention anything, we'll do the assumption that all costs are paid at the end of the year, and then we divide by 1 plus A to the power I. Okay, so here, since we don't have any notice about it, so we'll do some for I going from 1 to 20. Okay, of the cost per year, which is CI, over 1 plus A to the power I. Here, of course, they should mention for us what is the discount rate. Okay, so if they ask us to conduct the life cycle analysis, we need to provide the discount rate. So here we can say, for example, take A. So take A equal to 10%, for example. Okay. And the problem we did together last time about fuel, okay, they considered that we should pay the cost at the beginning of the year. That's why we divided by 1 plus A to the power I minus 1. But don't worry, in the exam it will be stated clearly. Okay, so if I don't mention anything, you consider over 1 plus A to the power I. If we say the cost should be paid at the beginning of the year, then you divide by 1 plus A to the power I minus 1. So now here we should just pay attention in part B to divide the cost, because it's not equal for all years. While in part A, it's much simpler. So if we consider part A first, so for part A, the life cycle cost, we have Can you tell me, do we have a missing information here in the given?
Salvage value.
Yes, in general, we provide the salvage value. Okay. If they don't give you the salvage value, then you don't, you will not consider it. But in general, they give us the salvage value for. But is it considered in the costs, the salvage value?
No, it's a return.
Yes, it's a return. So even if we have it, it will be added to the return part. Okay. So for the LCC here, we'll consider now for part one 12,000 because you have 3 kilowatt times 4,000 euros per kilowatt. So we multiply 3 by 4,000 plus. What is simple here is that the costs are constant for years. And for part A, you can take CI outside of the summation. So you just say it's 100 plus 150 times. You can use now the geometric summation. Okay, so you remember that we have already seen that the summation of from I equal 1 to 20 of 1 over 1 plus a to the power I, which is here 1.1, because a is equal to 0.1. So you can replace this summation directly by 1 plus a to the power n, so 1.1 to the power 20, minus 1, divided by I, divided by a, which is the rate, the discount rate, 0.1, times 1 plus a to the power n, so times 1.1 to the power 20. Okay, so in this way, we can calculate the value of the life cycle cost for part A. If we perform the calculation, we get for part A a value of $14,128.4. So of course, in order, we should make sure that the production will be able to compensate the life cycle cost of the system. So this is for part A. Now for part B, it is a little bit more challenging because we should divide the costs. For I, it remains 12,000. But now for the costs, we should do the following. For year one, so if we account for year one for the cost, we should add, they said that the operational cost will remain 150, but the maintenance cost will be 50. So for year one, we just have to add 50 plus 150. And because it's year one, and we'll assume, as we said, that we pay it at the end of the year, so we should divide by 1 plus a, which is 1.1, to the power 1. So this is for the first year. Plus, for the second year, we have, instead of 50 now, we have 75. So 75 plus 150 over 1 plus 1.1 square. And finally, for the remaining years, we just have to pay attention to do the summation now from year 3. So from year 3 to year 20. And for the remaining years, we'll have to add 100 to 150. So 100 plus 150 over 1.1 to the power I. In case we want to use the geometric series in our calculation, okay, You can do it on the calculator, but if they tell you use the geometric series formula to provide your results, all you have to do is to decompose this into two parts, because the geometric series formula will start from 1. You should say I can decompose this term into the following summation. The summation from 1 to 20 that I can calculate, but I should subtract from it, so minus 250 over 1.1 for the first year, and also I should subtract minus 250 for year 2, because they are not included in the summation. I just want the summation from 3 to 20. So I just have to subtract 250 over 1.1 and 250 over 1.1 square. And now I can replace this summation, okay, by 250 times the geometric expansion, which is 1.1 to the power 20 minus 1 over 0.1 times 1.1 to the power 20. Okay. And if I group my terms, so now I will have two terms multiplying the summation. Here because I considered, if you want, I summed already maintenance and operation in one term. So I will have this summation, but here I will have two terms over 1.1. So I should do this, which is 200 minus 250 over 1.1. So I will get minus 50 over 1.1. And here I have 225 minus 250 over 1.1 square. So in overall, if I replace, and if I group terms having the same denominator together, I will end up with the following formula. So I will have 12,000 minus 50 over 1.1 minus 25 over 1.1 square. Why I'm doing it general? Because I might use the expression for other questions. So always read the different questions to see if you need the general expression. And if they ask you for the internal rate of return, you need to have a general expression that you can use after by just replacing A by ROI. Okay, so plus 250 times 1.1 to the power 20 minus 1 over 0.1 times 1.1 to the power 20. Okay, now this is the life cycle cost for the two options, and we can of course here, because for the first 2 years we have a smaller cost, we can expect that this cost will be smaller than the one calculated in part A, and we'll get here for 14,062 0.3 euros. Okay, so this is the life cycle cost for the two options. Now let us consider a new question. So knowing that the number of operational hours, so knowing that the number of operational hours is 10 hours per day, Okay, we want to decide what should be the selling price in order to have a payback period of 5 years. So decide what should be the selling price per kilowatt hour, the selling price per kilowatt hour in order to have a payback period of 5 years. Okay. So now, if we consider they imposed on us the payback period that we want. So we need a payback period of 5 years. Okay. Then we can go back to our equation and we just can modify it in a way to serve our question. So of course, or LCC will have the same expression, but now because it's for 5 years, okay, so we just have to consider here to the power 5. So this is the only modification we should do for the costs. So here to the power 5 and here to the power 5. And as I told you, concerning the salvage value, as we mentioned before, the salvage value is taken into consideration at the end of lifetime. In some books, they consider, we included in life cycle cost, but we put it as minus. Okay, because it's an income, not a cost. But why we put it in LCC? Because we consider that it's equipment, okay, and we can get back a certain amount of its price at the end of lifetime. So in some formulas, we consider the salvage value even in LCC, but we put minus salvage value over 1 plus a to the power n, which is the lifetime. But of course, whenever we consider any year that is smaller than the lifetime, we'll not put it in the equation. Okay, so in case I give you the salvage value in this problem, you can include it in LCC, but you put minus, and you put minus salvage over 1 plus a to the power n, because you consider it's you can get back this money from the equipment. It's related to the to our initial investment, so we can get back a part of it. So this is a reduction of the cost if you want to consider. So if they gave you the salvage value in this problem, you can take it into consideration just in the first question by doing s over 1 plus a to the power 20. But whenever they ask you to find the payback period, which is for 5 years, then you cannot account for the salvage value because you cannot get it back unless you have you reach the end of lifetime. So pay attention when to consider the salvage value and when to remove it. You should only consider it when you do the calculation over the whole lifetime. And once they ask you to find the net present value or the value if you want the payback period, to calculate the payback period, you don't have to consider it because you assume that the payback period will be smaller than the lifetime. And here, for example, they told us we want a payback period of 5, so we should calculate NPV, okay, at 5. It should be equal to 0. And then because it's NPV at year 5, we don't consider the salvage value. So here they imposed on us the payback period, and we want to calculate the number of what should be the selling price to consider if we want to pay back our project in 5 years. So now we can use the LCC formula, but we should also make sure to consider the income. Okay, so they gave us the power of our system. It's a 3 kilowatt system. Okay, and they gave us also the number of operational hours. So when we multiply by the number of operational hour per day, so you have 10 hours per day. And since you want to find the production per year, okay, so you should multiply by the number of days per year. So let's say times 365. Okay, so this will give you the number of kilowatt hour. And then to get, if you want the money, your return. So your return, this number of kilowatt hour should multiply it by the selling price, S, which is in euros here, euros per kilowatt hour. Okay, so we will express our net present value function of S. So we'll write the following: the net present value, NPV, at year 5 should be equal to 0 in order to say that the payback period is 5 years. Okay, and now if we consider our previous equation, as we mentioned, we can have the same terms, but now we do to the power 5. Okay, and we should add now, we should consider, so this is minus, okay, because this is a cost. Okay, so minus this term, and now we will add to this what? We'll add the income. Okay, so plus, so let me write it again. So now all we have to do is to say that NPV at year 5, okay, is equal to minus 12,000 minus, already, يعني I will just put minus if you want for all terms. Okay, so we it was already minus for the second term, so now it's a plus 50 over 1.1 plus 25 over 1.1 square. Now, in the summation from 1 to 5, okay, you should include the value of income, RI, okay, and since it's a constant value as we calculate it together, we can take it outside of the integral. And here you have to add summation from 1 to 5 only, because we calculate the NPV until year 5 of RI, which is the income for each year, minus CI, which will account for maintenance and operational cost. And as we mentioned, we considered these two terms because the maintenance is different for the first 2 years. Okay, so plus summation of RI minus CI over 1 plus A to the power I. So here for CI, we already calculated the cost for the remaining year is $250. And it's a constant, we can take it outside. Yani RI also is a constant. We can take RI minus CI outside of the summation. And RI, as we mentioned, is equal to plus 3 times 1,000 times 365 times S, okay, times the selling price. And we can use the geometric series for the summation. So when we do from 1 to 5, so it's times 1.1 to the power 5 minus 1 over 0.1 times 1.1 to the power 5. And in this way, okay, in this way, we can calculate the value. The only unknown, this is equal to 0. The only unknown in this equation is the selling price. Okay, so if we perform here the calculation, we'll find out that the selling price to have a payback period of 5 years is equal to 0.31 euros per kilowatt hour. So 0.31 euros. Of course, to see if it's feasible or not, we should compare with the market. In general, what is the price of kilowatt hour in the market to decide if it's acceptable or not. So if we find it so high, so we say this price is really high, we can allow for a larger payback period because the lifetime is 20 years. So it's fine. Maybe if we have a payback period of 10 years, we will still be able to get gains enough for the remaining 10 years. So we can try to increase the payback period to get a more competitive price. And for example, if we do calculation for the value of the price, if we want to have a payback period instead of 5 years, let's say 10 years. Okay, so what should be as the selling price to have a payback period of 10 years? So now it's very simple because it's the same formula and we are just considering a parametric study. We are varying parameters. So here we are varying the payback period. So all we have to do is just to vary this term. So instead of 1.1 to the power 5, it's 1.1 to the power 10. And instead here of 1.1 to the power 5, also we can put 1.1 to the power 10. Okay, and we can expect then, of course, to get a lower selling price, because if we have a lower selling price, we need more time to pay back the system. So if we perform calculation for 10 years, if we have a payback period of 10 years, then the selling price should be 0.2 euros per kilowatt hour. And again, we should always make sure that we are able to be competitive with the market. If it's still larger, then we might say, no, we will not continue with this project. Okay. And after deciding on the selling price, we should calculate the CER. Yani now, once we decided on the selling price, let's say, we say for a discount rate of 10%, what is the CER? And we put always a target. If our target is a CER larger than 0.3, we should verify that the CER for this project is larger than 0.3. If it's not, we can go back to the project and try to see what can be done. As usual, we can try to search for, let's say, the same equipment, but at a smaller price. So we already discussed this. Maybe if it's made in China instead of being made in Europe, okay, while still having good characteristics. We can try also maybe to increase the number of operational hours without affecting the performance a lot of the system. And in general, the manufacturer can give you like a graph that will give you the efficiency depending on the number of hours of operation. So you can optimize the number of hours of operation in order to decide if you can increase the number of operation or not. You can also, so we already discussed that we can try to change the selling price in a way to be competitive with the market, etc. So you can perform a parametric study on all of these parameters in order to decide the best option. For example, if we opt for this selling price of 0.2 euros per kilowatt hour, to be able to calculate the CER, okay, when we go back to our formula, we should just pay attention first to calculate NPV at year 20. So what will change here is the summation from 1 to 20, plus what, in case they gave us a salvage value in the problem, we should add it, okay? So if we have a salvage value given, we add the salvage value over 1.1, but here they didn't give us a salvage value, okay? But in general, it will be given. So if it's given, as we mentioned, in the LCC, we subtract it because we consider it a part of the system. This is why we put it in the life cycle cost. And whenever we want to calculate the net present value at end of lifetime, we also consider it. So for the CER, if we do the calculation for this price, NPV at year 20 will be equal to, so NPV at year 20 will be equal to $4,590. Okay. So $4,590. So if we calculate the value of CAR, all we have to do is to do the ratio. Okay, and we get then a CAR of 0.38. So this value, sorry, do you see what I am writing? I think it will work.
Yes.
Okay.
Yes.
So
yes.
4,590.6 euros for the NPV, and for the CAR, all we have to do is to divide this by the initial investment. So this number over 12,000. So if our target is larger than 0.3, this is acceptable. We got nearly 0.38. Okay, so we have a gain of 38% of the investment, which is larger than 0.3. So this project is considered to be economically profitable. Now, if we aim for larger CAR, as we discussed, we need to consider several possible strategies, including reducing the investment, increasing the selling price, reducing maintenance, increasing operational hours, etc. Okay. Any question on this?
Professor, I have a question regarding the LCC, MPV equation.
Yes, tell me.
So here, minus LCC plus the summation of revenue over 1 plus interest rate.
Exactly. Yes, this is why the only modification of LCC, actually you take minus LCC, and because you will add to it summation of incomes RI from year 1 to year I to year N over 1 plus A to the power N, because already you did this summation, you can take it and factor with CI. And in general, when you add this to minus LCC, you can group two terms, which are some RI minus CI. Okay. So this is what you should subtract. You should subtract LCC from this term. And because in LCC you have minus I0 and minus summation of CI over 1 plus A to the power I, you can group the two terms together. And these two terms can be combined to replace by minus I0, okay, plus RI minus CI, and you can cancel out this term and just put here minus CI, okay, over 1 plus A to the power I. And don't forget to add the salvage value. So plus Cn, the salvage value, over 1 plus A to the power N. Okay. Any question on this? Okay, thank you. Bye-bye.